My name's Mark. I'm an astronomer here at Macquarie University. When I was your age, I had no idea I wanted to do astronomy, actually. I had a telescope, I did it as a hobby, but I couldn't imagine doing it for a job. Now I've got it as a job, I really like it. You get to think about interesting things, travel the world, talk to people from different countries, working on problems, working with them as well. It's really good. So here at the university I teach astronomy and physics, and I do research in astronomy as well. And I can't believe I get paid to do it because I enjoy it a lot. I get to think about really cool things and talk to people about really cool things like I'm talking to you today. So I'm going to talk to you about the black hole that's in the center of our own galaxy. It's called Sagittarius star. It's about 4 million times the mass of our own sun, which sounds like a lot, and it would be if it was kind of next door, but fortunately it's a long, long way away, so we don't have to panic about what it's going to do to us. But of course, there's a lot of interest in understanding how black holes work. They provide a lot of energy in the universe, and we'd like to understand how that works. So it's kind of nice that we've got one so big that's relatively close that we can study it. So I'm showing you now a picture of Orion, which is a famous constellation in the sky. If you go out in the evening, this evening, if it's clear, which it might not be, and just look over towards where the sun has gone down, you'll see this constellation. It's very bright. It's Orion. You've probably heard of it. I don't really want to talk about Orion today, but I just want to tell you how difficult it is to see our own galaxy from our place inside it. So we're on this little planet orbiting the sun, about 150 million kilometers away. The nearest star to us is much further away than our own sun. If you took our sun and put it far enough away, it would look like a star, but you have to put it a long way away. So I could talk in millions and billions of kilometers. That doesn't make much sense. It's much better to use how long light takes to travel places, to measure distances, because light travels very fast and the distances are very big. So it takes light 8 minutes to travel from our sun to us. It takes about 4 years for light to travel from the nearest star to us. And then from the center of our galaxy, where we'll end up taking a look, it takes light about 25,000 years to get to us. So it's a very, very long way away. Anyway, the problem with trying to study our galaxy is the space between the stars is filled up with dusty, smoky gas that absorbs a lot of the starlight. So when we look at the bright constellation like this, we're really not seeing very far through the galaxy. All the blackness you see here between the stars isn't because there's no stars in that direction, it's just the stars are blocked out. So I can show you the same view of the sky now, but changing to looking at some of the glowing gas near the stars. You can see this glow from gas that's being heated by some of the stars and then is glowing a nice red color. And that just shows you there's a lot of gas around, completely blocking our view through our galaxy. So in the olden days, well before my time, when the Herschel brother and sister, William and Carolyn, were trying to figure out the size of our galaxy by looking at all the stars and thinking about how far away they were. They didn't know about the gas, so they thought the galaxy wasn't very big at all. Now we know that the galaxy looks something like this. So we live in this flattened disk part of the galaxy, going in orbit around the center. And you can see where the sun is there, about 25,000 light years from the center. And you see where it says Orion spur, just underneath that. That's kind of where the stars of Orion are. So we're only really seeing that far with our eyes. So it's quite difficult if you just use your eyes or just use normal everyday light to get any idea of what our galaxy looks like. You have to change what you're doing completely. So I'm going to show you some maps of the sky now. So to get you used to that, I'm showing you a map you should already know. It's unfortunate Australia and New Zealand aren't in the middle where they belong, but as you know, this represents the whole globe of the Earth, the full 360 degrees, and so the left-hand edge and the right-hand edge are exactly the same. But this is looking down at the Earth. Suppose we look out from the Earth instead at the sky. We can make a similar map. So this isn't really a map, it's actually a whole bunch of photographs stitched together. And this has been lined up so the disk of our galaxy goes along the middle of the photo. And it's looking towards the center, but you can't see very much because of those big black clouds in the middle. Fortunately, it turns out that if you change the kind of light that you're using to look at the sky, so instead of just using the colors that our eye can detect, the red through to blue, we now move to infrared, which is kind of heat radiation, which has longer wavelengths, and it's not affected by the smoke that's mixed in with the gas in our galaxy, and we can get a much better view. So if we do that and look at the sky, this was taken with a satellite orbiting the Earth, you can see now the galaxy looks very different. You can see all the way to the middle. So this is the center of our galaxy right in that direction. You can see there's a little blob of stars in the middle. That's called the galactic bulge. And we live inside this thin disk-like part, and from our point of view it looks like you're just looking at it edge on because we're inside this kind of flattened plate that's the disk of our galaxy. You can still see there's some gas gets in the way even now, but most of it we can look through and get an idea of what our galaxy looks like. And then these fuzzy things here are the Magellanic Clouds, little mini galaxies that orbit our own. So you're looking at the light from thousands of millions of stars all blended together to give you this glow, right? And each of those stars is on its own individual orbit around the center of the galaxy. And the orbits are arranged so that everything looks tidy and you have this nice disk structure. But I want to talk about what's at the center of our galaxy, the very center. And this is the view if you use the light our eyes can pick up, the visible light. It's not very good. And so study of our galaxy really had to wait for the invention of radio astronomy back in the 1930s. And it turns out that radio waves, which is just another form of light, but very different wavelength, can get to us from the very center of the galaxy without getting blocked. So if you look now at radio, in radio light or radio waves, you see a very different picture. Now you can actually see the center of our galaxy in this small patch of sky in the constellation Sagittarius. And you see this glow in radio waves. Now, to you, this just looks like a funny orangey color. You should think of this as a black and white photograph, actually, but now in funny light that your eye can't see, but radio telescopes can. And the glow that's getting picked up comes from two different things. Some of it is from gas that's been heated by stars and is glowing. It would have been red in that Orion picture. So that's things like these. You can't tell, but I know this, so I'll just tell you. So this blobby thing here is ionized gas around a hot star, for example. And there's some other stuff like that. And then this thing here is something completely different. In this black and white picture, you can't tell the difference. If we had a color picture where the colors were radio colors, it would look a completely different color, and that's how we can tell what it is. This is an exploded star, and the explosion is barreling out into the interstellar space, and the blast wave is creating ultra-relativistic electrons that are producing this radio emission. So it's very different indeed. We see this whole mess of emission. I want to focus here at the very center of our galaxy here where it says Sag A. Inside here is a very interesting source. So all of these sources are kind of weird and interesting, and actually we only understand about half of them. We've got no idea what these funny lines are, these threads. We know that that's energetic electrons producing the radio waves, but we don't know what produces the electrons, so we just don't know. Okay, so now I've zoomed into the very center, just right in here. So now into the inner few light years of our galaxy, again in radio light, and now we see an interesting spot called Sagittarius A star, as well as some more messy looking stuff. Now the messy looking stuff turns out again to just be gas that's being heated by stars, but this spot is completely different. It's very energetic electrons, again producing bright radio emission, and it's very compact, it turns out, and quite bright, and so it was suggested very early on that this might actually be a black hole, but you can't really tell because you've just got this spot of bright radio emission. So it would be nice to know exactly what this object is and if it's really a black hole or not. It was only when astronomers started using infrared light to observe our galaxy that they could really start understanding what was going on here. So infrared light is like red, but it's redder than red. It's so red your eyes can't see it. So if you take a sunlight and split it up into its colors, you get a nice rainbow from red to green, blue, violet. But next door to the red is a color called infrared that your eyes can't see. If you stick your hand next to the red, you can feel the warmth from the sun from that radiation, but your eye doesn't see it. Your phone cameras can actually see some of it. So if you get your TV remote at home, it has a little glass bead on the front that you point to the TV and push the clicker. That glass bead sends out some infrared light to the TV and it sees the flash and it changes the channel or whatever. But your eyes can't see that. You have a look at it, you won't see anything. But if you look at it through your phone camera and push the button, you'll see the light come on, because the phone camera can see that light and make it visible to you on your screen. So try that at home when you get a chance. Anyway, astronomers use this because this light is also very effective at getting through the smoky gas that fills the space between the stars and our galaxy. So that lets us look close at the galactic center. So this is just a comparison of, if you look very close at the galactic center, what do you see in normal light? And you see stars that are very close and then nothing behind them, just black. If you look in the infrared, now you can see a glow from some bright stars in the very center of our galaxy. And this box is about the same size as that radio picture. I'll just flash back as that box there. So you can look very close. So I'm going to try and show you a movie that takes our view of the sky and zooms in closer and closer to the center of the galaxy. So now we're zooming in past some constellations in the sky, and we're at visible light now, so you can't see past these clouds. But what happens is we'll change to using infrared eyes instead of normal eyes, with telescopes of course, about now. And you can start to see the glow from the center of the galaxy. So we're looking closer and closer. So these are real pictures taken with real telescopes. They've been put together to give us a nice movie. And now you're getting very close to the center, about what we were looking at before. So you can see there's some bright stars there. Notice how they suddenly got sharp. That's because they're using adaptive optics to take out the twinkling of stars by our atmosphere. And now you can see the stars are moving around. So I have another movie to show you about that. This is important because we can see some of those stars orbit the black hole, and then that gives us good information about exactly where the black hole is and how much gravity it has that keeps the stars that are moving around it in orbit. You can see stars moving around. There's only a few frames here, taken a few years apart, so what you're seeing is how the stars change where they are over a few years. And you want to see this star going around and around, that's orbiting the black hole. And it gets very close to the black hole and speeds up because it falls in close, but it just misses and swings around and comes back out again. So this just shows you some of the paths some of the stars took over a few years. And because we have a good understanding of how gravity works, pretty much like in our own solar system, we know how orbits should be around things that are very heavy in the middle of the system, like the sun and so on. And so from all these orbits, astronomers, not me personally, could figure out that there was a very big mass just sitting right at this point where the hand is. Right? And that had to weigh 4 million times the mass of our sun. Because if it was less than that, the stars wouldn't orbit as tightly, they'd be much looser, or they'd escape entirely. So that is what tells us that this object is actually a black hole, because the mass has to be packed into such a tight space that the only way to do that is to have a black hole. If you tried to make it with something like lots of faint stars packed in together, they would just end up crashing into each other and merge, and you'd end up with a black hole anyway. So now we know there's a black hole there at the center of our own galaxy, and we know it's 4 million times the mass of our sun. Now, the question is, how do black holes work. So there's a lot of interest in this. I'll show you some movies. So what this movie is going to show is what happens to gas that gets captured by the black hole. Because we know black holes can be very energetic, putting out lots and lots of energy, and that energy comes from swallowing things like stars and planets and gas. And although eventually the material disappears through the event horizon and we never see it again, before it does that it tends to get very hot and glows, and we see the glow from the radiation. So there's a black hole here. You can't see it because it's black. And you're looking at part of a ring of gas. It actually goes all the way around. It's a complete ring, but they're just showing you 1/4. And this gas is in orbit around the hole. But so on the computer, they put the gas in orbit, but then they watch what happens to it. And what they find is that instead of keeping nice and smooth, it gets very messy and turbulent and jiggles around and spirals in towards the black hole. As it does that, it gets very hot. So it kind of feeds the black hole and glows, and we see that radiation coming out in the form of the radio waves we were seeing before. So there's been a lot of effort working out how this kind of thing works and what kind of light you would get out of the black hole and how it varies because of the jiggling around that you can see. There's bright spots and dark spots and so on. So that's one element of the work. The other interesting thing is whether general relativity, Einstein's theory that describes black holes, is actually correct or not. We've tested it many different ways, but not with black holes, which is a really strong test because relativity is very important there. Right, so one of the effects that black holes have is that they distort the structure of space and time around them in strange ways. One of the side effects of that is that light rays get bent as they propagate by the black hole. This is called gravitational lensing. It's just like whenever you take a funny thing that bends like a glass or a lens and look through it, everything looks distorted, and that's because light isn't traveling in straight lines. It just confuses your eye because it comes in from funny directions because of the bending by the lens. So this is a view across, it's actually in Washington DC, but it's a view of a nice building called the Castle. It's not a real castle though. From away. And now suppose we took the planet Saturn and we squashed it. Squashed it so hard that its density got so high that it collapsed and became a black hole. And then we put it halfway between us and that building. I'm going to show you what the lensing does. So the light then passing by that black hole we made out of Saturn gets deflected, and you get what's called a lensing effect. So the light, because it gets bent, it's just like you put curved glass there or something like that. You just get this tremendous distortion going on. So people have been interested in these kinds of effects around black holes, and I'll show you what this kind of thing does. So we're looking down on one of those messy gas disks where it's in orbit around a black hole. It's very messy and turbulent, and there's bright spots and dark spots, and you can see it going around. The black hole is in the middle, so you won't see that, and there's an event horizon or something here. And what we're going to do is look at this disk first from the top, and then as the movie goes on, we'll change the angle we're looking at it from. So we end up looking at edge on, and how much the disk is tilted will be represented by this blue bar, so it'll eventually go up to the top. I'll turn this on again, and you'll see that as we change the angle we view this thing at, the disk starts to look quite different. It starts to get bright on one side and dark on the other, and it starts to look very bent. So these are because the black hole is distorting space and time around it. So I can tell you why you get these two effects. So the thing looks brighter on one side compared to the other because the gas is swirling around. On one side it's coming towards you, and on the other it's going away. And it's going around very, very fast because it's close to a black hole. It has to travel close to the speed of light to orbit it when you're this close to a black hole. So it's really moving, and then it's glowing, but because it's moving towards you, most of the light energy gets thrust in your direction. It looks very bright. on the other hand, over here on the other side, it's going away from you, and the light is going in the other direction, so you don't see it. So you get this lopsidedness. The other effect is you can see that the disk looks bent here. So you'll see that as the tilt increases, so we look at the thing edge on, now it starts to look a little bit bent as well. And that's the gravitational lensing effect. So I can explain that to you too. So here's the black hole, my fist. The disk is nearly edge on. The reason it doesn't look nearly edge on is because of gravitational lensing. So suppose you were in this direction, looking, right? And you shouldn't be able to see the back of the disk at all because it's behind the black hole. But light can get bent, it can come up out of the disk and then get bent over the top and come towards you. So when you look back, you can actually see what looks like the disk up here, but it's actually down here. And that's that effect as well. So the idea here is by doing these kinds of calculations, once we get the technology to start looking this closely at the black hole, you should be able to see a disk doing this that's got these distortions, and that would be a tremendous test to see if Einstein was right, that the theory of relativity is correct. So there's a couple of different groups of astronomers working very hard to develop the technology to do this either with radio light or with infrared light. So recently there was a lot of excitement because a cloud was heading towards the black hole, and we're waiting to see if much of it falls in and makes the black hole get very bright or not, because now the gas will fall in, there'll be a lot of it. So you're looking at a movie, here's the cloud on its orbit, the black hole's in the middle here. You see the stars we were looking at before in their orbits. So this is just a cartoon, but it's a calculation of what happens. Here's the cloud, boom. It goes around, some of it gets captured by the black hole, so that gas will then fall in, and it might make the black hole very bright. So there's a lot of interest in seeing whether this will happen. You can see now it's 2030, so this has taken about 20 years to get this far. So there's a lot of effort kind of looking very closely to see now what that cloud is doing. It's just passed close to the black hole. That's right, so you can see the red, if you can see that, that's the orbit of the cloud. Again, the cloud, when it's far from the black hole, moves slowly, but it falls in, gets faster and faster, just misses and swings back out, a bit like a comet. Right. So the cloud kind of gets a bit destroyed by this interaction. It's not too happy about it. Now, most recently, last September, when they looked closely to see where the cloud was, they found it had moved from here to here to here. And it is doing what it's supposed to do, is to swing around the black hole. This red cross marks the position of the black hole. So they got the orbit of the cloud right, as predicted pretty much, and now the interest is what happens as the thing comes back, and whether this suddenly starts to get very bright here because the gas falling onto the black hole. So I wanted to show you this picture of the sky because this is very exciting. So now we're looking at the whole sky, but not in infrared or radio or visible. This is gamma rays, right? Gamma rays is a very energetic form of light, created in extremely violent events. And here you see the whole sky, and you can see they've blocked out the disk of the galaxy that runs along the central horizontal line here. And you see these big, what are called bubbles of emission. This is emission, again, from very energetic electrons. And it's thought this is a remnant of a giant explosion that happened in the center of our galaxy a few million years ago. The question is, did the black hole do that? Did it maybe swallow a lot of material and then explode? Or did something else, like lots of stars being created and then going supernova with their individual explosions, make it? So that's one of the big questions at the moment, is understanding whether this came from our black hole, that it doesn't just sit there quietly most of the time, but sometimes explodes, or whether this is something else. Anyway, I should finish there so that you have some time to ask questions. I think it's a long way from the center of our galaxy, and so I don't think it's anywhere close enough. So that particular object is safe. Those stars that are on very close orbits that we saw, they're pretty safe as well, but it is thought that now and again an unlucky star does get you have to get very, very close, it turns out, to be torn to pieces and then go into the black hole. So for a star it's harder to tear it to pieces because it's so compact, whereas that cloud is quite fluffy. So and so some of it got captured. The short answer is it depends. That's a good question though. So if you have a black hole and it's not capturing anything and heating it up and then swallowing it, the black hole itself doesn't emit very much at all. I say very much because I'll tell you it does a little bit, but classically in relativity it would not emit anything. It would just sit there and nothing comes out. Even when it's swallowing up these gas clouds or stars and they get torn and heated and messed up before they go over the event horizon, we see the glow from the gas. It's not really from the black hole itself, if you know what I mean, just from its victim. However, Stephen Hawking, you might have heard his name, he's a famous physicist. He came up with this idea that black holes actually could glow a little bit, and over time their mass would get converted to radiation coming out of the hole and they would disappear because they would evaporate. It was called black hole evaporation. It turns out that this is only important for very tiny black holes, much smaller than you would make with a star or this black hole at the center of our galaxy. But the effect is probably real. I say probably because it involves a mixture of quantum mechanics and relativity, and we don't have a full theory of that yet. But black holes do actually glow a little bit, but for a black hole the size of this or something, if you took Saturn and crushed it into a black hole, the effect would be invisible, it would be so weak. At some level we can't be sure because we don't know for sure what happens on the other side of the event horizon. Even though we have a theory that tells us most of what happens there, relativity, it's very hard to test that experimentally, which is what you'd like to do. It's believed that the matter just heads towards the very center of the black hole and gets crushed into a point that effectively has zero radius, called the singularity, where everything has to go. The question is whether that really happens or whether some quantum mechanical effect, which also always tends to smear things out, means that you have something with a finite size there. It's really hard to know for sure what happens. It's just very hard to come up with any way of really seeing. We can have ideas about what happens, but we can't test them properly because it's the event horizon. We get no information back from it. All we can tell is how much mass is there, how much spin there is of the material that went in, and how much charge it had. Those are the three things you can measure for a black hole: the mass, the charge, and how fast it's spinning. It's a phenomenon, as you know, called gravitational redshift, and it doesn't even have to be a black hole. Even here on Earth, time is running a little more slowly here on the ground compared to satellites in space. And that effect has to be taken into account to get things like the GPSs working correctly in our phones and so on. Fundamentally, it's the way that the black hole distorts space-time that gives you the effect, or the way even the Earth weakly distorts space-time because of its own mass that gives you the effect. And the distortion just happens to work in that direction instead of doing things the other way around. So, as I said, this black hole is at the very center of our galaxy, and it's 4 million times the mass of the Sun. So, there's a lot of gravity close to it, and of course, as you go away, it gets weaker and weaker. There'll still always be some small effect. But it turns out that there's much more mass in the form of stars and gas and dark matter, which is another question entirely, in our galaxy, so that the black hole's gravity is the most important thing within a few light years, but once you go a few light years away from the black hole, now there's more mass in just stars, etc. So the black hole's influence doesn't go very far in terms of its gravity. It's only a few light years, and we're 25,000 light years away, so that has no effect on us. If it blows up, like this bubble, Fermi gamma ray bubble, then of course it has a bigger influence, but it's not its gravity that's doing that, it's the light that it's putting out. It was a very strange result, this, because you expect, if you know anything about the orbits in our solar system, the planets that are further away move more slowly in their orbits and also have bigger orbits to go, so the time it takes them to go around is much longer than the closer planets. And that's what you expect if you have most of your mass in the center of the system. And that was supposed to be what happened for the stars in the disk of our galaxy. Because if you look around and see what you can see, you realize that most of the material in the galaxy should be close to the center. But when astronomers actually did the measurements, they found out that it did take things longer to go around, but they were moving just as fast as our sun. So it turns out pretty much all the stars that are orbiting further away from the center than our sun are all moving at about 200 kilometers a second, just like our sun. And that's not what you expect. It implies that there must be much more mass in the galaxy that we can see, and it's broadly distributed. It's still concentrated towards the center, but if you imagine asking the question, if I take a ball and center it on the center of our galaxy, how much mass is in there? And then I change the size of the ball to make it bigger and bigger. What happens to the mass that it's enclosing? Does it get constant, so I'm not getting more, or does it keep growing? It turns out it keeps growing, and that's what gives you that speed of stars in their orbits. You need that much gravity to hold the galaxy together. So it implies there's just that most of the mass of our galaxy, when you get to thinking about a sphere as big as the galaxy, is in something we can't see, which we call dark matter, mainly because of lack of imagination. We're not sure what it is. We know plenty of things that it's not. It's probably elementary particles that we don't know what they are, but we'll have to find out. So there's two things to calculate a density. You need the mass, how much stuff there is, and then you need the space, how much volume is it packed into. So the mass, I said, was 4 million solar masses, fine. Then we have to decide what we mean by how big it is. I guess we take the size of the event horizon, which is about 1/10 of the Earth-Sun distance for a black hole of this mass. So it's 4 million solar masses divided by the volume that would correspond to a ball with radius 15 million kilometers. So I can't do that in my head, but that's the sum that you need to do. So we see bright stars, right? Now, the black hole is so far away we can only see the very brightest stars. If you put the sun there, we wouldn't be able to see it. So most stars tend to be quite faint. So there's many more stars there than we can see. So you can make a guesstimate of that based on knowing how many bright stars versus faint stars. But then those stars would have planets and asteroids and things like that. And some of them will get loosened from the gravity of their stars. And they'll probably find their way into the black hole at some point. I'm going to get down to saying I have no idea, but at least I'm giving you some idea of the different things, it's like if you ask how many objects from space hit the Earth every day, the answer is it depends what size objects. Big objects, 10 kilometers across, thank heavens, don't come in very often, so only every 10 million years. Small things like grains of sand that still give you a shooting star across the sky as they burn up. You get many, many, many of those every day, like thousands, hundreds of thousands probably. And it will be the same will be true for this black hole. Thank you for your attention, everybody. I enjoyed that. I don't know if you did, but I did.